You ever stop and think about what makes a ball roll downhill? Or why a drop of food coloring spreads out in water? Or, get this, what actually powers your own thoughts? Well, it turns out they're all driven by the exact same fundamental, invisible force. So let's pull back the curtain on this hidden principle that shapes, well, everything. Okay, so take a look at this. You've got four different situations here, each with a ball resting on some kind of surface. Now, what do you think? Which one of these is truly stable? And the answer isn't just a simple physics puzzle, it's actually a clue that points to a universal law of nature that applies to pretty much everything. All right, to really get to the bottom of this, we're going to start with something we all kind of know, right? Probably from a high school physics class. It all starts with a simple ball on a hill and the idea of potential energy. Now, here's the thing. Technically, all four of these balls are in what we'd call equilibrium. They're not moving. But, and this is a big but, it turns out there are different kinds of equilibrium. The really important question is what happens if you give them just a tiny little nudge? And that leads us to our first type, stable equilibrium. Just look at case one. The ball's sitting in the bottom of that bowl. If you push it a little bit, what happens? It just rolls right back to where it started. It actively wants to be at the bottom. That's what we mean by stable. Now, on the flip side, you've got unstable equilibrium. That's case two. The ball is just perched precariously on top of a hill. The slightest, tiniest nudge, and poof, it's gone. It's rolling further and further away, and it is never coming back. That little disturbance just grows. So, what's the secret rule connecting all this? Well, it all comes down to one thing: potential energy. That stable ball, the one in the bowl, it's sitting at its lowest possible point. It has the minimum amount of gravitational potential energy it can have. And that is not a coincidence. This is a fundamental law of the universe. Systems, all systems, are always trying to get to their lowest possible energy state. Okay, and this is where things get really, really cool. Because this whole idea, it's not just for big things like balls on hills. It scales all the way down to the world of atoms and molecules. It's the same exact principle, it just goes by a different name. Yeah, check out this quote. It just lays it out perfectly. A ball rolls down a hill from a higher gravitational potential to a lower one. Well, it turns out molecules do the exact same thing when they move around, react, or melt. They're just moving from a higher chemical potential to a lower one. It's literally the same driving principle. All right, so let's nail this down. What is chemical potential exactly? A really good way to think about it is like a kind of invisible pressure. It's the thing that pushes chemistry to actually get going and happen. Okay, so the formal definition is the change in a system of energy when you add or remove particles. But I like the analogy of a compressed spring. A substance with a high chemical potential is just loaded with energy, ready to pop and change into a more stable, lower energy form. And look, the comparison to the ball on the hill just works so well. For gravity, potential depends on height and mass. For chemicals, it depends on stuff like concentration and temperature. But the goal is always the same. Everything is trying to find that lowest possible energy state, that point of equilibrium. Diffusion is a perfect, classic example. You drop some dye into a glass of water. At first, all those dye molecules are crammed together, right? That high concentration gives them a super high chemical potential. So what do? They spontaneously spread out, moving to areas of lower concentration to lower that potential, until everything is uniform. And it's the exact same logic for why ice melts. Once you get above freezing, those H2O molecules all locked up in that rigid ice crystal, well, they're actually in a state of higher chemical potential than they would be if they were just sloshing around as a liquid. So to find that lower energy state, they break free. The ice melts. It really is that simple. So the crucial point here is that this isn't just some obscure, abstract concept you'd find in a dusty old textbook. No way. This is an absolutely fundamental idea that explains a huge range of things we see and interact with every single day. I mean, its influence is just everywhere. We're talking about phase changes like melting and boiling, vital life processes like osmosis, and even high-tech industrial techniques like chromatography. The driving force behind all of them is just systems trying to minimize their chemical potential. And the guy we have to thank for figuring this out is the American physicist Josiah Willard Gibbs, way back in the 1870s. Now, his original definition is a little bit of a mouthful, for sure, but the core idea is so powerful.
He basically gave us the master key to unlocking all of these processes.
But now we're going to take this whole concept to its most profound and, frankly, mind-blowing application. And it's one that's happening inside your own head right this very second. So where does this all come together? Where is this hidden force having its most incredible impact on you and me? Believe it or not, the answer lies in this one tiny number, -70 millivolts. What is that? That's the average resting voltage across the membrane of a neuron in your brain. And this electrical potential, the very foundation of our entire nervous system, it only exists because of a tiny imbalance of charged ions, like sodium and potassium, that are all constantly trying to move from high to low chemical potential. In biology, they give this a slightly fancier name, electrochemical potential. But it's really just the total driving force on an ion. It's a combination of the chemical potential, which comes from the concentration difference, and the electrical potential, which comes from the ion's charge. And here is the absolute kicker. The flow of these ions, all perfectly controlled by the laws of electrochemical potential, is what creates the electrical spikes, the signals in your brain. Those signals are the foundation of everything. Every single thought you have, every emotion you feel, every action you take, it all comes back to tiny particles just rolling down their own little energy hill. So, from a simple rolling ball all the way to the very spark of consciousness itself, it's all driven by the same universal tendency to find the lowest possible energy state. It kind of makes you wonder, right? What other hidden forces like this are out there quietly shaping our entire world?